Hello, everyone. Our project is the virtual reality visualization for underwater autonomous unmanned vehicles. My name is Amanda.
I'm Catzby.
And I'm David. So for a quick overview of our project motivation, the main problem with data visualization right now is that not all data is 2D. So while a 2D screen may work for most forms of data visualization, when you're working with 3D volumetric data, like the ones we're working with right now, you're often missing features. As you can see, no matter which way you look at it, you're always missing part of the data. As you can see with the block on the left, you cannot see what details are on the back unless you turn it around. And there's also a need for immersive and interactive exploration of these data sets. So with that in mind, our goal was to develop an innovative and user-friendly VR visualization tool for 3D glider data from the Rutgers Center for Ocean Observing Leadership, also known as RU Cool. So for the data, the physical sensors are on the RU Cool submarine, which is seen down here. It then transmits the data to a satellite, which is then stores the data in a database down the road in the RU Cool Center. And then we pull from there to start visualizing our data. As for the visualization technology, we use the Unity game engine as well as the MetaQuest 3 for visualization purposes.
So I'd like to talk about the glider. So the mission of these gliders are to collect ocean data for a variety of purposes related to ocean monitoring, such as the viability of building offshore windmills or analyzing hurricane formation. So these gliders are integrated instrument platforms, which means it has a bunch of sensors that automatically collect data. And like David said, when they surface, they communicate with satellites to send this real-time data. So the way this glider works is that it takes data in water columns, which means it takes a sharp descent and ascent, and this picture shown, and it follows this pattern throughout the ocean. And it propels itself with a ballast engine, which takes in water at the top, which causes it to sink. And at the bottom, it empties its tank so it can float. And it also has flaps on the side, which controls the angle of descent. And the fin on the back controls the direction it flies.
So for a quick overview of our loading process, the first step is to choose the basic parameters. So this would be like a basic search engine. You put in the dataset ID, you will put in the variables of interest, and you put in the gradient file. Once all this is done, you run the program, and using this parameters, our application goes to the EarthApp API and pulls the necessary data. As you can see here, it is downloaded as a CSV file with all the necessary components. After that, we read the data into runtime variables, and then the gradients are also read in, and they're assigned to each of the variables, as you can see up here. So after that is done, we start the actual visualization process. We would plot our data in 3D relative to the world so that it is accurate, and the user is teleported to the side of the data. As you can see on the bottom left, the white line highlights our data, and you can see like the ocean, the seafloor, and even a mini map of where we are in the world. After all this is done, you can interact with the environment as if it were like a video game. You could toggle with different variables. You could explore the world, ride the glider, and save data subsets. And finally, after you're done playing with the world, you can end the application, and it saves the data sets you worked with for further use, just to save time so you don't have to re-download.
So I'd like to demonstrate the capabilities and features of our program. So when you're first loaded in, you're attached to the glider, which is why you're going up and down. And the menu in front of you shows the controls, which can be toggled to be shown or hidden. And you can detach from the glider, which is now seen. And you can also start and stop the motion of it. So now that you're detached from the glider, you can freely fly around the world using the joysticks. So currently the path is green, which represents time. And the name of this variable is shown on top, as well as the value of this variable where the position of the glider is. So you can also toggle through the variables, which changes the color of the path. And you can also change the way the data is drawn as a path or a wall of color. And the wall of color is to be able to show, to detect patterns and anomalies in the data more easily. And now we're flying above the data to show an overhead view of it and to show where it is relative to the world. You can also see this in the mini map in the top right corner. And the yellow marker shows where the glider currently is, and the red marker shows where the user is. It's hard to see, but you can speed up and slow down the motion of the camera as you fly around. And now we're flying back towards the glider. If you don't want to fly around, you can also reattach and detach yourself from the glider to return to the original position. So here, you can also speed up and slow down the motion of the glider as well. And this also applies to when you are attached to the glider, which is shown here. And the last feature we'd like to show is the ability to save points of interest to a CSV file. So currently you see a red laser, which is you point with one of the controllers, and you point it at the dots, which represent the data points. And once you've hovered over everything you wanted to collect, you press another button to save it to a file. And here we exit the program to show that you can access this data even after the program has exited.
For a potential application of this project, it can be used as a visualization tool for the RU Cool team. And throughout the summer, we discussed different implementation features for observing the data with the RU Cool domain expert, Laura and Josh. As you can see here on the leftmost corner, this is just the path of the glider shown as a line. And in the middle, you can see it as the wall of color. This project can also be used as a mission planning tool for glider deployments, as well as an interactive learning tool for students. Future plans and improvements that could be made towards this project would be optimization of data extraction and path creation, and of course, adding a gauge to display current data over there, and implementing ocean current patterns and visualizing marine organisms in the projects. Also adding a time scrubber for more flexible forwarding and rewinding of the project. For the acknowledgements, we would like to thank Yvonne Teskar, Jennifer Shane, and Wade Trappy for their guidance, as well as the researchers from RU Cool, Laura and Josh, for their data expertise. And this work was supported by Rutgers New Brunswick, CSI Scarlet Vision. Thank you. Any questions?